is the smallest positive integer, k, so that x to the power k is the unit. Okay? So, you've done this many times. Right? So that k here is the order of the element x. Right? Now, this theorem states that the order of x, in other words k, this k, divides the size of g. Yeah? Does that seem plausible? So I can reword that. So that x is just any element of your group. So the order of x, in other words, this little k here, the order of x is a factor of the order of g. Right? So the order of any element divides the order of the group. Now, how to prove that? Well, can you remember this from an earlier lecture? You need to go back a bit. What is this? This with the angular brackets? It's a subgroup. Now we proved that that you generate from this element. So now here's your group. So X is a generator to some extent. Maybe not the full group, but you can find all the elements going up to the kth. So that would be your first, second, third. That'll be your kth. So this here is the definition of it is it's this set, or actually, and you can prove this as a group. We did that part of the lecture. So this is actually a subgroup of G. Right? Okay. So that is a subgroup. Okay. We proved that in earlier lectures. Okay, so subgroup, and therefore its order, the order of this subgroup, divides the order of G. That's Lagrange's theorem. Right? The order of that group divides the order of your parent group. Okay, so what's the size of this? That's what this means. Size of, right? Well, what is the size of it? Well, just the number of elements in the set, right? Well, that's k. I mean, just count them. It's k, right? So the size of this is k, and that k is the order of x, all right? Now, this is a subgroup, so this subgroup generated by the element x. It's a subgroup G, and therefore its size, the size of the subgroup, divides G. That's just Lagrange. That's Lagrange's theorem. So the size of this divides this. Okay, but what is this? Well, it's just k. Right? Therefore, k divides G. But what's k? K is the order of the element, any element. Right? Therefore, the order of an element divides the order of the group. Okay? Again, a very powerful result. We will use, a lot of people, this is almost equivalent to this. A lot of people talk about this theorem, theorem 49, that the order of an element divides the order of the group. A lot of people sort of use this as they call that Lagrange's theorem. Now they're pretty closely linked, so right. But in the future we'll be using this a lot. Okay. All right. What's another? So another theorem is think about it. If the order of your group, not element, group, if the order of your group is a prime number, what does that say about the nature, the type of your group? Now, by using Lagrange's theorem, we can answer that question. Okay, so if you have a prime-ordered group, in other words, the group has its order of the group is prime, a prime number, then it's cyclic. So remember that any group whose order is a prime number, immediately you know that group is cyclic. Okay? Now how to prove that, right? Okay, so the order of your group is n, and let's assume n is a prime number. N is prime. Okay, so the only factors that n will have will be 1 and itself. By definition, it's a prime number. Right? Now, what subgroups have? Now, using this now, what subgroup has order 1? Well, just the trivial subgroup, where the set consists only of the unit. Right? It's the simplest possible group. It's just that. Right? That's the simplest possible group. It's called the trivial group because it's just so trivial. Right? All right. Okay. So if your subgroup has size 1, then it has to be this. Right? It's the trivial group. Now, if the other factor of n is n, like the full group. So that means any other element belonging to G besides the unit. Okay. It will have order n. Has to be, right? Because whatever the order is of an element, x to that k, whatever that order is, k, will give you e. Now, the orders of your element, because it's prime number, are 1 or n. That's all there are. It's a prime number. Okay. So the order of your elements, the other elements besides the unit, they have to be n, because that's the only other factor. If it's not 1, it has to be n, because it's prime. Okay? So the order of your element now is equal to the order of your group. K now is n. That's the only other factor possible. Okay? So that means that element, those other elements besides the unit, all their orders are equal to n. So each one of them is a generator of the group, right? Because this would be you wouldn't have k here. You'd have n. The full this would be the whole group. So this element here, which has k equal to n, the size of your group, this will generate the whole group. Okay? Therefore, by definition, that element is a generator. Okay? So if we can generate the whole group like that, therefore that group is cyclic. There's the proof, right? And another little one, I've run out of board before I stop. Let's assume that the order of the group, size is n. Okay, so for any element belonging to that group, x to the power n, the order of the group, x to the power is equal to e. Right? Now this is just a general group. It's not necessarily prime or anything. It's just a group. Okay? So let's take any element of that group, and it will have, the element will have its order, this k in other words. So x to the k is e by definition. That's the definition of the order of a group. All right. Then the theorem 51, states that k, that order, will divide n. That order there. The statement is this: x to the n is e. Now, k dividing n, we know that from previous. Here. Right? We know that from theorem 49. So the order of the element divides the order of the group. K divides n, right? So that means you can write n in this form. See, k divides n, so you've got some integer here, some other factor. So n is of the form ks. So these are two integers. So that means that x to the n is the same thing as x to the ks. Right? You just substitute for n here, ks. And you can rewrite that as x to the k all to the s. But x to the k is just e, right? Because this k is the order of the element, right? So that x to the k is just e, so you get e to the s, which is just e, and there's the proof here, right? So x to the n is e, x to the n is e. So there it is proved. All right. Next session, there's still one proof or so, plus a little bit more discussion. So I think I'll have one more session on the theory, and then we can do some problem solving.